Okay, I think we'll get started. We're here to talk to you today about Backpack. Backpack is a portable backend for your web applications. So we're going to start today by talking about what a backend as a service is. Then we'll move on to talking about the Backpack core application and API. And then from there, we'll talk about how we packaged up that single Backpack into a single instance architecture with containers. Then we'll move on to talking about how we built out to a multi-instance architecture, and from there, how we build an admin panel to work with our backpacks. There are two parts to an application. There's the front end part, which is the part of the website that you can see and you can interact with. And there's a back end that handles business logic and data. The back end stores the information that you need to display on the front end, and it handles changes in that information in response to user interactions from the front end. So what kind of data and business logic are we talking about? Well, a front end, for example, might prompt a user to enter a username and password. That information would be passed to the back end, where it's checked against stored data to determine whether or not a user is authorized to access the particular web page. Another example would be database management. For example, in a chat app, a front end might request the last 20 messages for display. The back end would look into the database and return those 20 messages along with any necessary metadata about which user added the message or when it was added, for example. The front end would use the metadata to display it in the correct order. A final example would be for file storage. So in a social media website, for example, you might want to allow users to upload a photo. So the front end could take that photo, send it to the back end with a request to save it, and the back end could store it in the file storage or whatever storage mechanism they're using and send a message back with a link so that the photo could be retrieved for future use. So those examples don't cover all of the complexity associated with building out a backend. In addition, a backend developer is going to need to handle a whole bunch of other issues like hosting, SSL certificates, data security, server configuration, real-time connections, and they're going to need to make sure that these features are all seamlessly integrated with one another and with the front-end code. That's a lot to deal with. It'd be nice to simplify things a bit so that the front-end developer has less to worry about. And that's what a backend as a service, or a Baas, is intended to do. A Baas is an application that provides an abstraction over all of the complexity of the backend. It encapsulates all of that functionality and provides a much simpler API interface for a front-end developer to interact with. With a Baas, instead of building out backend functionality, you interact with backend functionality via that API. So let's dig a little deeper into the concept of a Baas and how it works. So here you see a diagram of a typical architecture of a Baas-backed application. You have a front end that handles UI concerns. It could be on any platform, iOS, Android, or web application. On the back end, you have all the basic functionality that you need. These two parts interact via the API endpoints that the back end exposes to interact with the services it provides. Typically, front-end applications communicate with the Baas using an SDK. That's a software development kit. This can be written in the language of the front-end platform. So in the case of a web application, it would be a JavaScript library. The SDK provides convenience methods for interacting with the back-end API, and it exposes that functionality provided by the database, storage, authentication, or other services. So why would we use a Baas? It facilitates front-end development. It reduces development time, and it reduces the complexity, at least from the perspective of the front-end developer. So it would be good to use in a case where you want a development sandbox for trying out new ideas, where you're developing a minimum viable product, or for front-end developers who just don't want to worry about back-end concerns, or maybe don't have the skill to build out the functionality they need. So what are the trade-offs in using a Baas? Because it's not for every situation. It does simplify things, but that comes at a cost. So generally with these kinds of services, they provide an abstraction over the server and the back end. And the greater that abstraction, the less control you have over the server and back end functionality, but the faster you can build your app. So for example, with infrastructure as a service, the developer is responsible for everything from the operating system on up. That makes infrastructure as a service very low in abstraction, very high on control. With platform as a service, the service handles the operating system and some other basic things, as well as deployment. But the developer is responsible for all of the application code for both the front end and the back end. So this moves us up in terms of abstraction, but down in terms of the level of control compared to infrastructure as a service. Finally, with backend as a service, we take that abstraction one step further. So now the developer is only responsible for providing front-end code. So all of the services that the Baas provides are also made available. So there's much less for the developer to be responsible for. So one of the prime examples of a Baas is Google's Firebase. It's maybe the most popular Baas right now. There's also Amazon's Amplify, and there's a bunch of smaller providers as well. So why would we not use an existing Baas? Well, Firebase, Amplify, and all of the smaller providers all have the same sort of problem of being proprietary. So they're not open source, they're not customizable, and you have the problem of vendor lock-in if your application outgrows the Baas service. So we built Backpack to address those concerns. Backpack is a portable backend as a service. It simplifies backend functionality. It's easy to configure and use, so just like the proprietary versions. But in addition, it provides ownership and control over your data. It's open sourced, and you can host it wherever you like. We built Backpack for use on a development team that needs a sandboxed environment for front-end developers. So Backpack would be used in a situation where a single system administrator could set up and monitor the system with relatively little effort. And then that system would be available, provide easy access for one or more front-end developers who could then log on to the Backpack system, create their own Backpack backend, and then they would be able to work on whatever application they're trying out.
Thanks, Liela. Hi, my name is Holden Hinkle, and now we're going to talk about the Backpack core app and how we built a generic backend. The Backpack core app consists of several parts, which are all encapsulated in the green area shown here. The front-end application uses the Backpack SDK to interact with the backend, either through HTTP or WebSockets. And the backend exposes API endpoints that provide access to typical backend core services, which we'll discuss in the next few slides. The Backpack SDK is a JavaScript library with convenience methods for interacting with the backend API. This gives a front-end developer instant access to Backpack's core backend features, which include user authentication, file storage, data persistence, and real-time functionality. Every application needs a robust user authentication system so users can safely register, log in, and log out of an application. Authentication systems are complex and difficult to build. The Backpack SDK provides methods to easily add user authentication to a front-end app. Each Backpack comes with a users collection in the database, ready to go. After a user of a front-end app logs in and authenticates, the user receives a cookie with a session ID that is tracked in a Redis instance. Storage is another feature that is common to applications. Usually applications use a cloud storage system like Amazon's S3. One of the reasons we built Backpack is because we want users to own their own data and not have to use cloud storage. So we knew we had to build our own self-contained storage system. There are two common approaches to this. The first is to store files in a database. This provides data integrity, however, accessing files can be slow. The second approach is to use a file system. Storing and retrieving files in a file system is faster than using a database, but maintaining data integrity is more difficult because metadata can't be stored with the file. We considered these trade-offs and decided to go with the latter approach. We store files in the local file system and metadata for each file in a database collection. The next component we'll talk about is data persistence. This was tricky because we needed to create a generic data management system that is super flexible because we don't know what kinds of data a front-end developer will want to store or how they'll want to model it. Backpack uses a NoSQL Mongo database because it provides that required flexibility for our use case. Using MongoDB, front-end developers can create schemaless data collections so they are not constrained in any way. However, sometimes a schema is necessary. The JavaScript Mongoose module allows us to enforce a predefined schema for the user's collection, which stores usernames and passwords, and a storage metadata collection. That brings us to our next topic, routes. How do we create routes for accessing resources that don't exist yet and are unknown? We needed to create a way for front-end developers to access the data in the collections they create. Normally, these routes would be hard-coded. You'd have a name for a collection of data, like photos, for example, and define your routes based on that collection name. So what happens when a front-end developer creates a new collection like cars? We generate all of our routes dynamically. When the Backpack core app spins up, it iterates over all of the collections in the database and dynamically creates the routes. What happens if the front-end developer creates a new collection while the application is running, though? That's not a problem. The routes for the new collection are created at runtime. The next challenge was to create generic real-time functionality. But first, what's real-time? Real-time refers to the ability to send information to a server or from a server to other connected devices the moment something happens. Real-time communication is ultra fast. You can send and receive data at the same time, and you could receive data that wasn't explicitly requested. Why would you need real-time communication though? Real-time communication is used in all kinds of applications, from chat apps to multiplayer games to social feeds and collaborative editing apps. Backpack uses WebSockets for real-time communication. WebSockets are like HTTP in that they're both a communication protocol over TCP/IP. However, unlike HTTP, WebSockets provide full bidirectional communication between a server and a client. The connection is persistent and stateful, and communication can happen in near real time because the connection doesn't have to be reestablished for each request. This diagram illustrates the differences between HTTP and WebSockets. The left-hand side of the diagram illustrates what's known as the HTTP request response cycle. The cycle is always initiated on the client side in a web browser. The client makes a request which is sent to the server, and the server processes the request and answers with a response that is sent back to the client. The right-hand side of the diagram illustrates a WebSocket connection. To create a WebSocket connection, the client first sends an HTTP GET request to upgrade to a WebSocket connection. Then the server approves the request and the WebSocket connection is established. The key difference to note is that with HTTP, information can't be sent from the server to the client unless the client first requests it. With WebSockets, on the other hand, both the client and the server can freely send information. So how do front-end developers normally work with WebSockets? On the back end, there are all kinds of things that need to be considered. For example, how do you set up a WebSocket server? How do you deal with authentication via WebSockets? How do you broadcast messages or HTTP responses? And how can you create and manage user channels? And lastly, how can you interact with the database? On the front end, there are other things that need to be set up. For example, how do you create the initial WebSocket connection? How do you deal with connection failures? And then for each thing that you need to have happen over a WebSocket connection, you need to code those things up yourself. And all of this is a lot of work. So how do front-end developers use WebSockets with Backpack? It's much easier. On the back end, just about everything is taken care of for you. The WebSocket server is set up, authentication just works, channels are available, and messages are broadcast to the connections that should receive them. On the front end, you're given a set of comprehensive generic SDK methods so you can do just about anything you need to do for WebSockets.
Okay, so we've explained how we put together our backend API, but this architecture would be a pain to set up every time you needed a backend. You'd have to install Mongo, you'd have to install Redis for session caches, you'd have to make sure you install the right version of Node to run the API. You'd have to set up environment variables to tell the API how to interact with Mongo and Redis. So this isn't very helpful if we're trying to make it easy on the front-end developer. So we needed a way to package our Backpack instance and make it easy to use. So our challenge is, how do we package our Express API, database, and dependencies for easy deployment wherever? And the answer to this is containers. So why would we use containers? Well, containers are a tool to package an application with its dependencies. So that means the Mongo and Redis instances that we need get packaged up with the API code and can all be installed in one bundle. Containers provide an isolated, consistent environment. So consistent means that every time you load the container or the containerized environment, you get all of the dependencies and their correct versions. And it's isolated in that it doesn't really interact with your host system. So whatever version of Node you're running in your host machine, it doesn't matter. You can run a different version of Node inside the container environment. It does make use of the host operating system for kernel tasks, but otherwise it's independent from the host OS. So in this way, it's similar to a virtual machine, but it's lighter weight. So here's a comparison between virtual machines and containerized applications. So on the right, you have the virtual machine. So living on the host machine, which is sort of represented by the yellow, and the host machine's infrastructure is available. There's a hypervisor that acts as an intermediary between the host machine and the virtual machines. And then you see the virtual machines in the sort of beige color on top. And inside each virtual machine, you've got application code, but you also have to install a full guest operating system. On the left, we've got containerized applications. Again, they're living on the host machine. They have the host machine's infrastructure. They also can make use of the host machine's operating system. And we have the Docker daemon installed to manage the containers. Then we have the containerized applications, again, in the beige boxes. But you notice in this example, we have only the application code running in each container because each container can make use of the host operating system. That means that containers use fewer system resources and they're faster to spin up, which is great because part of what we want to be able to do is spin up a backpack on the fly. So how do we go about containerizing Backpack? Well, containers are meant to run a single process per container. So we're going to zoom in here on just the container operating in its host machine. So again, we have the infrastructure, the operating system, and Docker. And then on top, we have a single Backpack instance. So Backpack has 4 components. It has the Express API that we explained earlier that handles the application code. It has the Mongo server, which handles database interactions, which is the database for storing data. And it has the Redis database for session caching. So each of those is a separate process. And then in addition, we have an Nginx web server that's kind of off on its own that handles front-end hosting. So each of these is a process. Each of these needs to run in its own container, which means a single Backpack instance requires at minimum 4 containers. So here you can see the single Backpack instance is sort of noted by the dotted lines, which is a way we're going to a thing we're going to use throughout the rest of the presentation. So if we have all these containers living on the host machine, that's great, but they can't just live independent of one another. They need to communicate. So Docker provides networking capabilities. So we have a bridge network that we use to connect the Express API to the Mongo server and the Redis session cache. Notice the Nginx server isn't connected over that bridge network because it doesn't actually need to interact with any of the other components. Also, Docker allows us to map container ports to host machine ports. So we have a port exposed from the Express API and from the Nginx web server to listen to requests from the internet. So how did we do all this? How did we coordinate these services? Docker provides what's called a compose file. It's basically a configuration file where you provide service specifications for application components. So we have 4 components in our system that we've outlined, and those 4 together make up a single application. So the service specifications are how those services are going to interact together. So the Docker compose file allows us to name the services and then explain explicitly how we're going to expose ports, what volumes we need for storage, environment variables that are necessary, and it also allows us to define the interactions over the network that these different components are going to use. So that's great. We have a single working containerized Backpack instance, but our actual goal is to support multiple backpacks. So we're going to talk about how we went from the single instance to a multi-instance architecture. So the question at this point becomes, how do we support easy deployment of multiple Backpack instances within a single Backpack system? We saw 2 options for building out our system this way. One is a multi-tenant architecture where a single Backpack instance provides backend functionality for multiple applications. And we also thought maybe we could use a multi-instance architecture where we have a different Backpack stack or a different Backpack instance for each application using the system. So we're going to talk about both of these in a little more depth. This diagram represents the multi-tenant architecture that we considered. So in this diagram, you can see on the top, there are 3 applications using our Backpack system. And those 3 applications are all interacting with a single Backpack instance, again, denoted by the dotted line. So all 3 applications are sending requests to the same Express API, and then we're using a single Mongo server to handle data for those applications. We also have a single Redis cache, Redis session cache, and we have a single Nginx web server for hosting. So in this setup, routing is a little complicated because we're going to have to hit that API with requests from all 3 applications, and then have a way of determining which application the request is coming from and how to handle the request accordingly. So this would involve either handling it based on the URL or with unique API keys, but it would have to be written into the API code. We also have an issue where if we need to have administrative tasks, for example, the front-end developers who are working on these apps might need to inspect their data or create a new application in our system. We're going to have to add specific API endpoints to handle those administrative tasks. These new API endpoints are going to require their own authentication system and maybe even a new administrative database. When it comes to scaling, because the Express API is stateless, we can scale horizontally if we need to grow. Mongo also supports horizontal scaling either by replication or by sharding. So that was the multi-tenant option. Now let's consider the multi-instance architecture. So in this setup, again, we've got 3 applications using our system, but now we've got 3 independent Backpack instances handling requests. So 1 for each application that's using the system. So like app 1 is going to hit the system and all of its requests are going to be sent to the app 1 Backpack instance, which has its own API, Express API server, its own Mongo server, its own Redis session cache, and its own Nginx front-end hosting. This is going to require, though, a reverse proxy to route requests to the appropriate Backpack stack because we can't handle that in the application code anymore. We're also going to need an admin panel for managing the system since individual Backpack stacks will need to be spun up and managed. And that's going to require a network for handling communication between the new components in the system. As far as scaling, we can spin up a new Backpack for each new application, but we're going to run out of resources on our server at some point. So we're going to need a way to manage containers across multiple servers. So how do we decide? Let's look at these again. So on the left, we have the multi-tenant architecture where we have a single Backpack instance handling requests from multiple applications. In this case, we have a simpler architecture because we just have the single Backpack instance. But the downsides of that are that we have overloaded application code trying to handle routing and administrative tasks as well as handling backend functionality. We also don't have isolation between the applications using the system. They're all being handled by the same database. Scaling is a little complicated in this architecture as well. On the right, we have the multi-instance architecture, where each application using the system has its own Backpack stack, its own API, Express API, and its own Mongo database. This version offers full isolation, so the code for each application is completely independent of the other applications. It's a little easier to scale because we just have to spin up a new Backpack instance for each new application. And it respects the separation of concerns. So app code only handles backend functionality. It doesn't try to handle routing or administrative tasks. But the downside of that is that we need additional components. So we have a reverse proxy for handling routing and the admin panel for administrative tasks. The other downside of this model is that now we're going to need a container orchestrator to manage our containers.
Okay, thank you, Liela. Hi, everyone. My name is Ido Moskovich, and I'm the third member of the Backpack team. So we felt that the costs involved with building a multi-instance system were well worth the benefits that Liela just covered, especially given the availability of existing networking and container orchestration tools. So our challenge becomes, how do we take our system from here? In a quick review, this is our single instance Backpack deployment that we have so far. There's the Express API running on its own container. We have our Mongo database and also the Redis session store. And those three different containers are all communicating with one another over a backend network. And then we have this fourth container running Nginx as a web server that can host static files for like a front-end website. The API and Nginx are both exposing ports so that they can handle requests that come from outside of the Docker system. So how do we go from here to here? And what this is one server that is now somehow running multiple Backpacks on it. And in order to get here, we have to figure out how to basically package up the existing system into a single logical unit that we can then spin up on demand or tear down. But once we figure that out, that's going to introduce some additional problems that we'll have to solve in order to make this work. For instance, how do we deal with routing in a system like this? This is a slightly more complicated problem that we'll deal with in a lot more detail, but if we have multiple Backpacks all exposing the same ports, all running different web applications, how do we make sure that the system routes requests to a specific application to the right Backpack? The other challenge that this introduces is how do we scale this out? So eventually, if we keep spinning up Backpacks on one server, it's going to run out of resources. So there's two options typically for scaling, and one is to just keep pouring money into the server and continue to upgrade it in a process called vertical scaling, but that gets very expensive pretty quickly. Or the other alternative is to scale out horizontally instead and figure out some kind of way to run Backpack across multiple servers. And that's what we wanted to try to do here. So this diagram is illustrating three different servers. each of which is able to run multiple backpacks. So if we want to get here, this adds even more complexity to the routing issues that were introduced with the previous architecture. But even this isn't exactly where we want to end up if we want to build an effective system to scale horizontally. We'd like to try to get here, where instead of deploying full backpack instances to the various servers that are a part of our system, we'd like to be able to run individual services that are a part of each backpack across these different systems, because that lets us do some nice things, such as maybe have one server that's a little bit beefier than the others. Maybe we can put all of our Mongo services running for each of these different backpack instances on there, because they might need more resources, versus our Nginx container, which probably doesn't need quite as much power to be able to run effectively, and we can just host that somewhere else instead. Now, getting to here, where we now have multiple servers hosting individual components of each backpack, is only going to make our networking challenges even harder, because now we somehow have to coordinate these containers across different machines. So getting here introduces this kind of to-do list that we'll have to walk through in order to effectively build a system that looks like that last slide. So we started off with figuring out, how do we spin up and tear down individual backpack instances, what we're calling stacks here. Once we figure that out, can we then get to spinning up these instances across multiple servers? And if we do that, that's going to involve this other to-do of, can we manage communication across these different servers? Once we handle that, we have to go back to that routing issue and say, how do we take a request that's coming from the internet, from outside of the system, and send it to the correct backpack within the system? After we get all of that done, how can we make it easy to do all of this, so we don't want to reintroduce all of the complexity that we were hoping to solve with the system by making the deployment really difficult? And then finally, if we're going to split up these backpacks across multiple servers, if there isn't going to be a centralized place where all of the data for all of these different backpacks is going to live, how do we give front-end developers access to administer their backpacks? So to handle this first to-do, spinning up and tearing down backpacks, we relied on something called a container orchestrator. And here's the definition of a container orchestrator from Docker. It's a tool to manage, scale, and maintain containerized applications and the networks they use to communicate. So unfortunately, this is one of those definitions that kind of requires definitions for each word inside of it. So we'll unpack this over the next few slides. But before doing that, we chose to use Docker Swarm as our container orchestrator. There are two popular ones, Docker Swarm and Kubernetes. We chose Swarm since it's built into Docker by default, so that helps us eliminate a dependency of our system. It's a bit simpler to use than Kubernetes, but still handles everything that we would need from the previous slide. So we thought it would be a good choice for our use case. So jumping back into this definition, the first part of this that we'll cover is, what is a containerized application? And in Swarm terminology, a containerized application is called a stack. And the stack would represent each of the different components that need to be working together in order to have kind of a single fully running application. Like in this case, it would be our API plus Mongo plus Redis plus Nginx and the backend network that they use to communicate. We can define a stack using something called a stack file. And this is really similar to the compose file that Liela introduced, but it is structured a little bit differently for Swarm instead. And the stack file, again, defines what are the different components, so which services are going to be a part of this application, where each service kind of represents one of these containers. How should that service be deployed? So do we want multiple instances of each service running? What environment variables should we pass into these? Which networks should each service be joined to? All of these tricky installation and deployment details can be defined using the stack file. We can take the stack file and pass that in as an argument to the different command line commands that Docker exposes for interacting with Swarm. So by combining stack files with Docker's CLI, its command line interface, we're able to check off our first to-do. We have some way to package our Backpack stacks as containerized applications, and we can use Swarm in order to spin them up or tear them down as we need. To get to this next step, we'll also rely on Docker Swarm to be able to spin up our system across multiple servers. So Docker Swarm has this concept of nodes, and a node is nothing more than a server that is joined to the swarm. There's two types of nodes. There are manager nodes that handle all of the deployment and management issues that come when you want to spin up a stack. So they're kind of responsible for figuring out where different services should be deployed and how to spin them up. And the second type of node is the worker node. And worker nodes are responsible for actually running the services themselves. So when we spin up a Backpack on a swarm, and let's use this as an example where we have one manager node and 4 different worker nodes that are all part of the same swarm, Docker Swarm will figure out, okay, where should I deploy each service that is defined in this stack? When we first add a stack, maybe the manager node is going to kind of load balance each of the services across the available worker nodes. So here we can see that it chose to put each service on a different node. So now this introduces the question of, well, if all of these services are a part of the same stack, they're supposed to be working together as part of a single containerized application, how do they do that if they're running on totally different machines? And to solve that problem, Docker Swarm introduces something called an overlay network. And it's a virtual network that kind of exists on top of all of the different worker nodes and manager nodes that are joined to the swarm, and which lets services communicate with one another based on the names that they're given in the stack file. So here, despite the fact that each of the services in this single stack are running across different worker nodes, using overlay networks, we're still able to manage communication between them. So as we spin up additional stacks, we can see here that Swarm and the manager nodes will just keep figuring out how to deploy the services for each stack based on the available resources across these different nodes. So we can see here that it doesn't matter how different these configurations are, whether we have all the services across all the nodes or for one stack, if it has all of its services just running on one. For the purposes of the swarm, we can continue to treat each of these containerized applications as a coherent logical unit. So that takes us through our next 2 to-dos. Using Swarm and its concept of worker nodes and manager nodes, we can now deploy our system across multiple servers. And with the help of overlay networks that we can also define using Swarm, we can still manage communication within our stacks. So now we can get to that tricky issue that I've been putting off, which is routing requests from the internet to the right Backpack. So earlier, when we were talking about the single instance version of Backpack, Liela said that we could expose ports from the services that are running within Docker to the host machine. And this would allow requests that were coming from the host machine from outside of Docker to make their way to the right container within the host machine. This works really similarly in Swarm, but because Swarm is built to run across multiple computers and have, multiple servers, each of which can have multiple services running on them, it needs a way to provide some kind of abstraction that says, we're not going to expose the port to a particular server because you don't know which services are running on that server. Instead, we'll expose just one big network that's kind of on top of the entire swarm. And when you publish a port, when you say that this service should listen to requests from port 3000, that publishing is going to happen into this network and not individual machines. So that additional network that lives on top of this whole system is called the ingress routing mesh. And here's just a quick diagram of how this would look if we had one Backpack running in Swarm across all of its different servers, it still kind of looks like a logical unit. We could have it expose a port, still port 3000 through the ingress routing mesh, another port 3001 for Nginx. And regardless of which server gets hit by a request, Swarm will figure out how to route it correctly through its routing mesh. The problem with this is that we want to be able to support multiple Backpack instances. And each of these instances, each of these stacks, is defined by a stack file that says that the Express API is listening for port 3000 requests, and the Nginx web server is listening for requests from port 3001. Unfortunately, you can't have multiple applications or multiple processes listening to requests from the same. This conflict basically means that we can't do what we were doing before by exposing individual backpacks through the routing mesh. A common solution to this kind of problem is to use a reverse proxy instead. So rather than exposing services from each backpack through the ingress routing mesh, we'll instead put a reverse proxy that's sitting in front of all the backpacks. It's going to listen for requests that come through the routing mesh, and it will figure out then, how do I route this request to the appropriate backpack? And the one additional component that we'll have to introduce when we create this reverse proxy is another overlay network, because this reverse proxy will need some way to communicate with each backpack stack. So by introducing a reverse proxy, by joining it to an overlay network that is then joined as well to the relevant services on each backpack stack, we've found some way to solve our port conflict problem, but now we have a new problem, which is related to service discovery. So if a developer spins up a new backpack on a running system, how do we tell the reverse proxy about that new backpack? It's going to need some way to say, hey, I know that I should field requests for this new backpack and pass it along. But the problem is that typically reverse proxies work with these configuration files that you have to specify before you spin up that proxy. So in this case, we might have a rule using subdomains that say, if the swarm receives a request for app1.domain.com, then the reverse proxy will look at that subdomain, app1, and pass it to the backpack stack that also has that same name, app1. So in this instance, if somebody spins up a new backpack, we would need some way to either dynamically update the configuration file being used by the reverse proxy so that it can update its rules and know that it should field requests to it. But that would then require usually restarting the reverse proxy so that it can pick up the new configuration, which would lead to downtime and just sounds really complicated. So we want to try to avoid that kind of scenario. And thankfully, we can by using a specific type of reverse proxy. And this one's called Traefik, with this little gopher guy is their logo guy. So Traefik is a reverse proxy that's built specifically for containerized applications. And what that means is that it can ping Docker Swarm for updates about which stacks are running within Swarm. So as a developer spins up a new stack, we're able to dynamically update the routing rules within Traefik to make it aware that it should route requests to that specific stack without restarting and without requiring us to manually manage configuration files. The way that this would work is that when we ask a developer to spin up a new stack, it'll be as simple as giving that stack a name with a form such as the one you see on the left. When they do that, that name will get assigned to the stack itself within Swarm, and it'll also get used within the routing rules that we can pass to Traefik so that it knows to handle requests for that specific name. And with that, we've checked off our next to-do. By using Traefik as a reverse proxy, joining it to each backpack stack with an overlay network, we are now able to route requests from the internet to the appropriate stack within our Swarm. There's just one more benefit that we get from Traefik that's important to cover, and that's SSL. So we talked about how we want to offer user authentication to front-end developers through the core API, and that comes with a lot of security implications. And one of the things that we really don't want to do is to pass sensitive information like user passwords over unencrypted communication protocols like HTTP. And the common solution for that is to encrypt that traffic using the HTTPS protocol. To do that, you need to get something called an SSL certificate, and that needs to be issued by a certificate authority. So this comes with a whole host of challenges, especially for us when we don't know where developers will be hosting our system and which domain names they'll be using to host the system, because these are all details that you need when you request an SSL certificate. But fortunately, by using Traefik, we're able to configure it to automatically request SSL certificates based on its configuration when it spins up, kind of regardless of how it's initially set up by the containers. So just a quick aside there, our last two steps are to make it easy to actually spin up or tear down our backpacks. And finally, to give our front-end developers who are using the system a way to actually manage their individual backpacks, to see the user data that's associated with backpacks and also any of the actual application data that's been generated for their apps. So building the admin panel. We talked about how we have currently a way to manage our stacks using these command line commands plus these stack files, and that gives us a way to spin up or tear down backpack stacks. Unfortunately, this isn't a very easy system to deal with. So it's going to require some security problems, such as giving front-end developers root access to the servers running Backpack so that they can run these command line commands. It would require typing, which everyone hates, memorizing commands, arguments, other environment variables, managing the stack file, and all of that is just not going to lead to a very good or secure user experience. So what we wanted to do is to abstract all of this behind an easy to use graphical user interface in our admin panel. The admin panel would let front-end developers register and sign in as administrators. It would let them spin up the backpack stacks with that user-friendly name, what we were looking at before with Traefik. And it would also let them remove backpack stacks. So if they're done working with a specific application, if they were just testing something and want to tear it down, we wanted to give them a way to do that very easily. And here's what we came up with. So we've got our admin panel on the front end. We would build some kind of backend that would handle requests from the admin front end. That would then be able to communicate with Docker through its CLI, and we would have the stack file available to that process. And so as the administrator took different actions from the front end, it would be able to handle these different stack management tasks. And in order to provide some visibility to the front end user about what was going on with the stack management, we would pipe the standard output and standard error from the Docker CLI back to the front end so the administrator could confirm that things were spinning up or tearing down correctly. And so here's kind of what this looked like in an early prototype. We have our name, we're filling out our backpack, and then we can see that the CLI is piping these commands back to the front to actually show that, yes, we were able to spin up this lol service, and then here we're deleting the backpack one. So to build this out, we have one more stack that we built, one more containerized application. We have our front end that we're hosting with Nginx. Over on the left, the bottom left, we have another Express API that we're hosting as the backend for the admin panel. That is then communicating with a Postgres database, which we're using to keep track of the front-end developers who are signed in as admins. And then finally, one more Redis instance that we're using to track session storage. So when admins sign in or sign out of the admin panel. So we have the stack, and then we put it together with our existing system like this. So we've got Traefik, our reverse proxy, sitting at the very kind of front of the swarm. It's handling requests from the internet, basically. It is also joined to the admin panel, which can handle requests that go to admin.thedomain.com. And then anything else, any of these other subdomains, Traefik will route to the appropriate backpack. that takes us down to our very last to-do, which is to somehow connect this admin panel to an individual backpack to let the front-end developer interact with the data inside of it. Right now, our Express API for the core Backpack app has the ability to deal with collection management. So the application data that's been stored in a backpack, we have different endpoints that we can use to interact with that. We have a way to register users and log them in, which is great if you're a user of a backpack and want to start using that. But we don't have a way for, let's say, an administrative type of user, the front-end developer, to do any kind of user management. So to see, okay, who are my users, to necessarily delete users, or just do some of the other tasks that an administrator might do with the users in their application. So that's a problem because we want our admin panel to provide those kind of administrative tasks. So let's say that we wanted to bypass the Express API because it didn't have these user management capabilities. We didn't want to build in those user management capabilities into the Express API because those didn't seem like very secure functions to expose kind of as APIs to the internet, at least not without some even more complicated authorization systems. So one option that we had was to maybe connect the admin stack directly to the Mongo instance of a backpack so that it could interact with the user collection kind of regardless of what the Express API for that backpack was allowing. The problem with that is that the Mongo database isn't actually exposed to anything outside of its individual backpack stack. The only thing that can interact with it is this Express API that's also a part of that backpack. And we felt like this was a good architecture, a good way to secure the data within the database and also confirm that there's only one way to interact with it, which is through the application code. So we didn't really want to do away with that necessarily. So what we had to do is to create some other way for the admin panel to communicate with the Express API, to build the user management functionality into the Express API and only expose it to the admin panel. And to do that, we ended up with this architecture where basically the admin panel is joined to one more overlay network, and that overlay network connects it to each of the Express APIs running on each backpack. So the way that we secured this is that each backpack is now going to listen to requests from 2 ports. The first port is going to be connected to Traefik so that Traefik can keep routing requests to it from normal everyday backpack usage. The second port is only going to be exposed to the admin backend. And so when an admin wants to review the data in their backpack, the backend will send that request to the specific backpack. That's going to create a WebSocket connection that gets proxied back to the admin. And that persistent connection will then expose some of these additional user management tasks that we wanted administrators to be able to handle. And so through doing that, we're able to check off the last to-do on our system here, our last architectural to-do, and have each of these kind of ready to go. And that's how we built Backpack as a portable backend that can support multiple backends from one deployment. This is a little snapshot of what we look at. Thanks so much for joining us, and we're happy to take any questions you might have. Okay, so we have one question. Was there consideration to using the multi-tenant architecture, but creating instances of an admin panel to create separation of concerns? I think that we did give that some thought for sure. We were a little bit more concerned about the isolation issues with the multi-tenant architecture. So this, again, was the system where we would have one Express API and then kind of one Mongo server, each with a database for each of the different backends that were running from it. And we felt like the isolation issues there were compelling enough to simply explore a different architecture to start with. So we didn't go too far with seeing how we might be able to make the multi-tenant architecture a little bit easier to work with from the administration perspective. Great. Liela or Holden, you want to take the next one?
Yeah, as far as the licensing, I think all Capstone projects are licensed under the MIT license. So it's open source, but it's not GPL.
Great. Okay. We got another question. Does the Backpack API allow devs to configure the resources for each container in an instance? Like if I want to give my MongoDB or Redis container more memory or CPU. So that is something that we listed as part of our future work. Because we're using Docker Swarm, and because we have each of these services running in their own containers, it wouldn't be too complicated in order to say that, hey, this specific backpack is getting, let's say, a lot of requests to hit the database. Let's try to scale out its specific Mongo instance across multiple services. That would be relatively straightforward to do, but it's not something that we've built into this first version quite yet. Okay, well, I think that that's it. Thank you guys so much for your time. We really appreciate it. If you have any other questions, we're around on Slack all the time. But thanks again. Hope you have a great Friday.